Hi, higher level. We're now going to take a look at continuity and differentiability, which are pretty easy ideas if you understand the idea of limits. The function is continuous at some point, x equals a, if and only if all of the following are true, that the function is defined at a and a is an element of the domain, that there's a limit at a, which means the limit from the left and from the right exists and they're both equal to each other. And both of these things are equal to each other. Here are some examples of discontinuity. We may see a hole because the function isn't defined at that point. We may see there's this jump happening because the limit isn't defined. As I approach a from the left, it's not the same as I approach a from the right, so the limit is not defined. Or you may have this hole with the function defined, but defined at a different spot. So the value of the function in that third picture doesn't equal the limit, even though they both exist. None of those three examples are continuous. You may have different definitions of continuous, whether you're looking on a specific interval, if it's everywhere in the given domain, or if it's all throughout the real numbers. If there's discontinuity at any of these points, you would just state where it's discontinuous or change the domain. I think it will come pretty naturally based on the way the problem is phrased of whether this means everywhere in the real numbers or if it's continuous at a specific point or a domain. I don't think you need to spend a ton of time kind of memorizing all of these different definitions. Here are, again, a few examples of discontinuity. That removable discontinuity we saw where the function doesn't equal the limit. The jump discontinuity where the function jumps from one spot to another, perhaps on a piecewise function. And the infinite discontinuity, here's just another way to look at having something that's not continuous here. That's, again, though, because the limits aren't the same. So it's very similar to B in this sense because the limit to the left is not the limit to the right. So the limit doesn't exist at that value. We're going to take a look at a couple examples here. I have a piecewise function. So if x is between -1 and 1, I'm defining my function to be -2x. And anywhere else, so whether it's exactly equal to -1 or less than -1, or exactly equal to 1 or more than 1, it's going to equal 2. You can see it graphed on this coordinate plane. Is it continuous at x equals 0 and x equals 1? You may be able to kind of determine it from the graph, although holes especially might be kind of challenging to see on a graph. At x equals 0, the function is continuous because that 0 as an x is always going to be on the linear function -2x. As I approach it from the left and as I approach 0 from the right, they're both going to equal 0. The function equals 0 there. I don't have any issues with the domain, so this is continuous. However, it's discontinuous at the point x equals 1. It's jump discontinuity because as although you have the function defined here, I say, okay, well, x equals 1, I'm using that f of x is equal to 2 otherwise. So it's defined, but the limit doesn't exist because as I approach, can I get my highlighter? As I approach x equals 1 from the left, I'm approaching -2. And as I approach x equals 1 from the right, I'm equaling +2, so the limit doesn't exist. So it's not continuous. Here's a bit more of a complicated function. Again, a piecewise function. When x is equal to -2, the function equals -3. It's just a coordinate point. And otherwise, I'm going to define it by this kind of funny rational function that I've created, really just to show you different examples of continuity, discontinuity, etc. Here's a graph of it. You may be able to understand just also by knowing that you can't have 0 in denominator, that we may have a hole there or something funny might be going on. Those could be possible points of discontinuity that we'd want to look at. Maybe it's clear on the graph, maybe not. So x equals 3, x equals -2, and x equals 1 are all going to give me possible issues that I should look at for discontinuity. At x equals 3, we have a discontinuous function because while the limit exists, as I approach x equals 3 from the left, it's going to 1/50. And as I approach it from the right, it's going to 1/50. So the limit is defined there. That could be found using the algebraic properties of limits that we talked about just before, canceling out the x minus 3. G of 3 is undefined still because in my piecewise function, it doesn't tell me what to do other than this otherwise function at x equals 3, and I have a problem actually in the original function. I'm dividing by 0. So the function doesn't exist there, so it's discontinuous. However, we see something based on this silly little definition I gave my function. Although the limit as x goes to negative 2 does exist, here's my negative 2, as I approach it from the left and I approach it from the right, it's going to negative infinity, so the limit's defined there, although kind of weirdly. And my function does exist at x equals negative 2. It equals negative 3. Those aren't the same thing, so it's discontinuous. And in the last one, we have the issue that the limit just doesn't exist at x equals 1. As x approaches 1 from the left, we're approaching negative infinity, and as we approach x equals 1 from the right, we're approaching positive infinity. So it's discontinuous. Differentiability is very similar. Not only does a function have to be continuous at a certain point to be differentiable at that point, or continuous overall to be differentiable overall, the derivative must also exist and be continuous over whatever interval or domain is given to you as well. You may see this on an original function that might have like a corner going on, really tight turn. It may have this jump discontinuity or a vertical tangent. So the vertical tangent is, of course, a problem because you're looking at a vertical line, which won't really have a clear slope there. So here's an example of one type of function that's not differentiable everywhere, the absolute value function. Because the absolute value function is kind of like a piecewise function, where as long as x is less than 0, it equals negative x, and if x is greater than or equal to 0, it equals positive x. It is continuous. The limit exists. Both sides, they're equal to each other, and the function is defined there, and those are equal, but it's not differentiable because of this corner. If I take the derivative of both of these pieces separately, I get that the first piece of the function, x less than 0, has a derivative of negative 1, and the second piece has a derivative of positive 1. And if I approach this value of 0, x equals 0, from the left, it's going to negative 1, but if I approach it from the right, it's going to positive 1. That should say positive 1. The limit doesn't exist, so the derivative is not continuous there, okay?